Good morning, everybody. Thank you, Mr. Chairman. And many thanks to the organizing committee to the possibility to show here some results about my work. So I will present here the possibility to define quantitatively differences among limousine enamels and modern one by using non-invasive techniques and X-ray by using X-ray fluorescence analysis. Okay, let me some time to introduce my co-worker, Dr. Maurizio Aceto, professor at the University of Eastern Piedmont in Alessandria, that worked with me in the force analysis on these kind of materials. And Dr. Simonetta Castronovo, curator and conservator at the Museo Civico di Arte Antica in Turin, Italy. So, a brief introduction about this work and the materials that I analyzed in this work. The collection in Piedmont is due to several metalworks composed of Limoges enamels that are held in museums and churches of Piedmont. Most of them can be related with the so-called treasure of Gualabicchieri, that is a rich complex of coffin medallions and other jewelry works gathered by Italian Cardinal Gualabicchieri during his travels all along medieval Europe. According to the written records, there should exist at least 5 scrini or coffini di opera Lemovicensi, presented by Gualabicchieri to Sant'Andrea Abbey, founded by him in Vercelli. Some medallions from this coffret were most probably cut off, successively sold in the antiquarian market and eventually reaching their final destination in museums all over the world, such as the Louvre and the Musée National du Moyen Âge à Paris, le Musée du Picardie Amiens, the Metropolitan Museum of Art in New York. Besides this, a number of modern copies of Limoges works are produced in the 19th century, following the great revival of this enameling technique. You can see there, okay, the woodland church in the San Sebastiano Church in Biella, where some of these medallions are held. So, you can see here an example of 2 different medallions. One of the problems is to define the authenticity of these medallions. For example, between, as this case, to the same subject. Okay, from the iconographic point of view, you can see there are no differences or apparent differences. In this work, I take in account some limousine medallions and some medieval enameled objects to show the possibility of a test fast and accurate to discriminate among medieval and modern manufacturing. Obviously, one of these medallion is modern and the other one is ancient. But you can see that the iconographic object is the same. The used color are quite the same, dark blue normally and turquoise or light blue. There are other examples where also light green colored are used. These are a simple case because the differences are easily defined by an expert conservator, but some cases are more complicated due to the bad conservation of the objects, for example, or due to the use of a renameling process where some parts are removed and other parts substituted by a modern mixture of oxide, for example. There are some cases where, for example, a Christ figures was used in a new, old Christ figure was used in a new enameled object. And this is very difficult for a conservator to know if the total part of this object is really modern or ancient. So the aims of this work is to discriminate among original medieval limousine metalworks and 18th and 19th century scopies. We start defining a qualitative approach to search differences in elemental composition of the metallic alloys and in the difference on the enamels. But we need a research to obtain numerical evidences, for example, by means of a quantitative approach to this analysis. We cannot carry on with the use of 1, 2, 3 croix to define the concentration of an element inside an enamel. We need numerical data to compare results with other scientists or with other people. So it's necessary to introduce some detail on the used technique. I used a energy dispersive X-ray fluorescence, portable X-ray fluorescence. This is one of the equipment used. You can see we work directly on the site. And we can work with the possibility to see quite all the elements present in the enamels and in the alloys. The limitation is in the sodium concentration. The depth analysis of this technique is around 100 microns, 150 microns, and depends from the kind of material analyzed. Okay, I don't know if you know the X-ray fluorescence analysis, but it's very simple. There are some X-ray that go to the object, and the recorded X-ray can to define the elemental concentration inside the object. So I used the Louvre collection, la collection L'Arcade, as an excuse to present this technique compared to all the others analyses made in Piedmont. So here you can see, for example, 2 analyzed medallions of the collection L'Arcade. The collection L'Arcade, consisting in 12 enamels, freestanding medallions, supported on copper-like metalworks realized with a so-called Champlevé technique. The appearance of these medallions from what that concern the metals are gilded. And here you can see an example of a typical result, qualitative result of the analysis of this medallion. I focus my work in this discussion on the blue enamels because I needed the same color in all medallions analyzed. Okay, you can see here that the amount of calcium, silicon, and lead is not so big as you can see in this picture, but is around 10%. The typical composition for the blue enamels is in these elements, where you can see both antimonium and thin elements as opacifiers. And the copper alloy is a mix of copper, essentially, and some impurities of zinc, iron, and lead. The gold alloy is from an amalgam process with using mercury. Okay, but this is not sufficient to define a composition. We need numerical data. To make this, I used a mixed way by using also a fundamental parameter approach and an empirical approach. We preferred to use this mixed model because it reduces the error in the data obtained by this technique. Someone yesterday asked me if this technique is semi-quantitative, quantitative, or not. This is not the point. We need numerical data. We try to reduce the error in this data, and we search to obtain so-called quantitative results. To make this a big work to define the standardization process was performed. We analyzed glass, metals, alloys, and also film to define, for example, the gold thickness on the metal part of the medallions, and to obtain, for example, the mercury amount in this amalgam. The results of this work is exposed in this table. So it's not so simple to read this, but there are an homogeneity in the data. This is the first result. After, you can see that contained in silicon oxide, this is around 50%. The lead oxide below 10%, more or less, and values on the cobalt is the colorant agent in this case, obviously not in the green, is around 0.15. All these data are compared with the unique data that I found in literature. Is this the results performed by Biron by means of electron microscopy, where microanalysis, where you can see the obtained concentration. So that's are the results obtained by XRF. So there are some differences, this is true, but are quite comparable. Okay, probably the content in lead is not so good, but other results are absolutely comparable. But this is not sufficient. We need to compare this data with a large amount of data, because we need to obtain a statistical approach to this problem. To elaborate in a statistical way the result, we need to perform a lot of analysis. In this picture, you can see the numbers of analyzed samples. This is only a part, because this is the first part of the work. The last part performed in the last month is more expensive, in time consuming. Okay, this is only to define the encoding of the samples. I defined the San Sebastiano medallions in the Church of San Sebastiano as SS. In the coffret of Museo Leone are ML. The medallions to the Civic Museum of Turin are PM. And okay, this is the code of the Louvre collection, of the Lacade collection, and this is the Coffret of Santa Caterina in Vercelli. Okay, I present now some results about these enameled materials, metalworks. The Santa Caterina, the Museo Leone Coffret contain 15 medallions placed on on the side and on the top of this coffret. The realization is similar to the medallions of the L'Arcade collection, and probably this coffret belonged to the treasure of Gualabicchieri. The results are similar, where the content of lead and calcium are quite the same. Change the content on iron and copper that are higher instead respect the L'Arcade collection. This is the Santa Caterina coffret. This is, you can see, casket belonging to the treasure of Gualabicchieri Bishop, and it is constituted by different named figures in three sides of it, and a rhomboedral drawing in the back side. We analyze all the parts of this sample, of this object. The results are a little bit different because, so for what that concern lead and calcium is the same result. For what that concern the content of tin and antimony, we have more antimony, the amount of concentration of antimony. Okay, we discuss after all these results from the quantitative point of view. Okay, this is the so-called Cassa di Gualabicchieri on the Museum of Turin. We analyzed also these medallions and also the freestanding medallions, not all ancient, but some of them are modern in the Museo Civico. You can see a comparison of a medieval and a modern medallion. Here you can see the arsenic contained in this medallion that can differentiate the two objects. Also the content of cobalt that is higher in respect to the old one. Okay. This is the last example, are a series of medallions in the San Sebastiano Church, are inserted in its wood chorus, are 18 Limoges medallions that remains of the 29 reported in previous historical reports. The medallions are composed by a copper-like metal with layered gold, and the enamels are realized by means the same Champlevé technique. There are some discussion about this series because, for example, Barbara Bones suggests to analyze them because probably are modern. Okay, we made it. And the results are show that in effect are modern. You can see the arsenic amount here and the potash concentration here that is higher in respect to the, for example, the L'Arcade collection. Okay. You can see the L'Arcade collection where the potash is lower and we have the absence of arsenic. There are only impurities of arsenic in these medallions. But there is a strange medallion, the number SS22, where the composition is like to the limousines medallions. And we think this is an authentic medieval material. Okay, about that I need to give you some data about the composition of ancient glass. This is not my field of expertise, obviously, and you are probably more expert than me. But I would like to underline the absence of quantitative data in literature. In spite of a lot of work of Stapleton, Biron, Wypicki, Tait, or others, so, the number of quantitative results are few. This is a resuming table of all these works. You can see, for example, about the arsenic used as a pacifier instead of thin antimony can detect the 19th or 18th century manufacturing. The presence, for example, of high content of lead as instead of the use of fluorescein agent and a pacifier too. We can see a summary of the results. Okay, we can compare the Louvre medallions with the modern copies in the Palazzo Madama, the Museo Civico of Turin, where you can see the amount of the lead concentration in the Palazzo Madama copies and the reduction of the content of silicon oxide. The same is for calcium, where there is a reduction of the amount of calcium in the mixture because we use lead or potash. And for what concerns the opacifiers, there are the substitution of tin or antimony with arsenic element. The same is for fluorescein agent, where, sorry, there are some problem. Okay. Where the amount of potash increase in the modern one. And also in the colorant agent, there are some differences, for example, on the cobalt content that increase up to 0.607%. And there are also the presence of chromium. This is not so strange because it's already reported in literature, but is one element that defines the modern manufacturing of these objects. Now we are able to perform a statistical approach to compare all the data recorded just up now. We used a principal component analysis where we defined a number of samples and also we define a number of variables. And we create a matrix where we can realize our statistical approach. The results are defined here. Also, it's not so clear, I'm sorry, but we can define in this way. There is a group where the concentration of lead and cobalt is low, and where the concentration of arsenics is quite transcurable. And are the Palazzo Madama, the Museo Civico di Torino series, the original one, and the l'Arcade collection. There is here a group where we can include the Museo Leone series as some of the Santa Caterina samples, where the concentration of thin is higher. And the last group is the San Sebastiano series, where the arsenic, the potash, lead, and cobalt is higher instead of other groups. The only difference is due to the SS22, that the composition is similar to the Museo Leone series. So when Julia correct my paper about so the standard abstract suggests me to define the three groups as medieval, limousines, and modern enamels. But I'm not so sure, because it's too simple to define in this way this kind of differences. Because we can have differences in composition also due to the not only time, but also in location of the materials. At now we can define differences from these two groups and this, modern or ancient, but this difference is not so clear. We need more data to define that this is older and this is younger materials. So all the results, all the analyses are performed also in other colors. Here is reported the turquoise, where the colorant agent is the copper in this case, but the differences are the same. Lead, high content of lead, for example, in these modern medallions is the same observed in the blue, in dark blue color, and also the content of arsenic or the increasing of the potash content. The distribution of these medallions is, the color of these medallions is quite the same as reported in the blue, dark blue analysis. Some differences are present also in the metal analysis, where in all cases we observe copper. These are all original, and the presence of brass in the San Sebastiano series. This is the bigger difference between this series. And from what that concerns the gilding process is the same. I can report here the increasing of mercury in the modern, sorry, the opposite, decreasing of the mercury concentration in the modern medallions, in the modern laminas. This is the resuming table about the SS23, where we can see the high concentration of zinc. And so I quite finished. I can, to conclude, it has been shown a non-destructive, non-invasive in situ analytical methodology to discriminate between large series of samples. The Larcad collection metalwork seems to be similar to B of the 13th century. The application of in situ X-ray fluorescence analysis could be competitive with this microscopic microanalysis approach. See that the features of new silicon drift detector, for example, and the fundamental parameters model in this kind of study are improving. We record all data for all. This is only an example. We can discuss after it's better. But you can see, for example, the SS series where the content of silicon oxide is decreased and the lead oxide is over the 20% in concentration, and also the concentration of the copper oxide. The cobalt oxide. So there are all data that we can discuss if you want personally. So I would like to some thanks to all people that permit this work. For example, Isabelle Biron, the Paul Getty Conservation Institute, and so all people that work with me in this project. Thank you so much.
Yeah. Thank you so much, Dr. Agostino. In a way, it's good news knowing that there is non-invasive possibilities which are available, at least to us, to distinguish. This is kind of good news. I forgot to mention that we, of course, are a discussion meeting. So we want to talk to each other, and of course, this lecture, as all the others, is open to discussion. We have a microphone somewhere, so there's a microphone. So if you want to discuss anything, just wave your hand, and I see the first question with Hannelore.
Well, thank you very much for this very interesting talk. You have a very impressive set of data, and it's great that you can play with the numbers and do statistics. That's really very impressive. We just came back from Corning, from our glass ceramics working group meeting, and there we were discussing extensively about the reliability of XRF handheld data. And so I just wanted to ask you what you think about how did you do your standardization, how, about the quantitative results, and how did you really do your standardization? What is your margin of reliability? And then also if you compare with SEM, where there's striking differences, do you have examples where you can really compare it? Or is this something where we are still in the dark about really XRF and SEM, where with XRF you always have to consider a certain depth of information and all that?
The problem is the real concentration of one sample is 1. I can analyze them with SEM, XRF, other technique, but the results, I think, should be the same. For what that concerns the XRF analysis, the problems are we cannot use fundamental parameter as proposed by manufacturer or manufacturing, or industries, because don't work. If I press button in my XRF and I take data, quantitative data, directly, the results are not so good. If you use standards, You can increase the affidability of your data. But there are some problems due to the technique. For example, you need to take in account of all elements contribution and all elements influence each other. And this is not possible. Yes, is it possible using standard? But you need a lot of standard, thousands of standards. It is really impossible. I propose here a mixed model. You can use a fundamental parameter and also an empirical approach. It's not my idea. There are people that work in this way. Sitko, for example, or Van Espen is in the group of Van Grieken. Are people that work in the XRF approach, Janssen too. So I think this is the way to obtain good data. For SEM analysis, I think there are the same problems. You cannot use SEM, push the button, okay, this is the concentration. It's not so simple. You need to discuss the data. There are models also for SEM analysis. If you don't know this model, you use, for example, 15 keV to analyze your sample instead of 20, your model change. But if you don't know that this model change, your results is wrong.
Yeah, I think this is a kind of very good warning that it's not just press the button, and so it needs definitely, this method needs expert advice. Absolutely. And you have to be really aware of the advantage and disadvantage. So what are you exactly measuring, from where deep it comes from? I think for comparison you really have to have comparable data. Exactly. This is also, you have to have comparable data which you really can compare. I was particularly interested in hearing about the chromium. So there was always a tiny bit of chromium in this blues, and why is that so? Is that just to give it a little hue in the color, or so? As I got it, consistently in all the modern things, you had some chromium in it.
Yeah, but this is not so strange because Lipinski write about that. It's here. It's true. Because I read it, but
I should read more of your papers, Mark.
Yeah.
Sorry.
What is the explanation of this composition? I don't know, because we are searching the impurities inside of a mineral used in this.
So you think it's not intentional, but it's just
I think no, but I'm not. I am an expert in XRF, not in.
Mark, any opinion?
It's hard to say. It's always very, very small amounts.
Yeah.
Thank you. Yeah, it's always very small amounts, so it's not clear why it's there. But I don't think it's accidental, because it's in a time when the chemistry was better known and they were using more purified materials.
Yes, the use of more cobalt means that was used more mineral containing cobalt, and you know that there are also bismuth or maybe chromium.
Well, you also showed that you had less iron in the later cobalt blues.
Sorry, you have?
Well, you showed you had less iron in the later cobalt blues versus the earlier ones. So the only thing I can think of, the chromium is adding a yellowish, greenish tinge, which the iron would have added. So
Okay.
they're taking the iron out, possibly adding a bit of chromium.
Maybe. We performed also, I don't present here this measurement, the force analysis, our fiber optic optical analysis on the color to distinguish different color and different absorption of different elements inside the exist differences between the medieval and the modern. So it's not the same blue. Maybe.
If there are not any urgent questions, we are absolutely in time. And let me thank you once again for this wonderful start of the meeting. Thank you, Dr.
Thank you so much.